Welcome back. This is homework set 32. This is the homework associated with that lecture on stability and center of mass. These problems are in chapter 9, and we're looking at problems 15 and 33. Problem 17 was worked in all its gory detail in the lecture, so I'm not going to work that problem. Let's look at problem 15 though. This is problem 15 in chapter 9. We have three objects, and the first object is located at the origin of our coordinate system, and it has a mass of 4 kilograms. And the second object is, it has a y coordinate of 1 and an x coordinate of 0.8, and it's 10 kilograms. And then we have a third object that's right here on the x-axis, and it has a mass of 6 kilograms. Now we're using as our method of finding the center of mass, that's the goal of this problem, is to find the center of mass of this system of three objects. It's a weighted average. The x position of the center of mass is just going to be the position of the first object weighted by its mass, plus the position of the second object weighted by its mass, plus the position of the third object weighted by its mass. And then we have to divide by all the weighting factors, M1 plus M2 plus M3. And that's going to give us, we've got, this one has an X value of 0, so that's going to be 0 times 4 kilograms, just wasted ink. This one has an X value of 0.8 meters times 10 kilograms. And this one has a X value of 2 meters, and it's 6 kilograms. And now we have to divide by the masses, and that's going to be 4 kilograms plus 10 kilograms plus 6 kilograms. And when I do that, I'm going to get 8 plus 12 is 20, divided by 20, that's going to be 1 meter. The kilograms are going to cancel out, and I'll get 1 meter. Now in the y direction, I've got the same formula with x's replaced by y's. So I'm going to have 0 times the 4 kilograms, and I'm going to have 1 times the 10 kilograms, and I'm going to have 0 times the 6 kilograms, and then I have to divide by the weighting factor. Well, 4 plus 10 plus 6 is just 20 kilograms. And so what you see is that I've got 1 meter times 10 kilograms over 20 kilograms, that's going to be 0.5 meters. So that means that the center of mass is going to be right there. Okay, and that would be the weighted average of the mass in this system of three objects. Okay, that's been problem 15. Again, problem 17 is worked in the lecture. I hope you're going and watching those lectures. That's still a very important part of the class, even though we can't meet together in that lecture hall. Let's look at problem 33. Problem 33 is a mix of old and new. It has rotational kinematics in it, where we use the kinematic formulas, the 4 kinematic formulas, and then it has a kind of a look forward towards the idea of torque that we'll be covering next week in lecture, but you've already had it in your reading. So let's look at that problem 33. We have a wheel, a pulley if you will, and this pulley has a radius of 0.2 meters, 20 centimeters, and it has a string wrapped around it, and this string is attached to a block, and that block is allowed to drop. And we're told in the first part of this problem that it starts from rest and it makes 3 complete revolutions in a time of 4 seconds. Okay, so if we make our list of the 5 variables in rotational kinematic, we have the angular displacement, the angular acceleration, the initial and final angular velocity, and time. And you remember that the name of the game, same as in linear kinematics, is to find 3 of these from the problem statement and then use our equations to solve for the others. Well, we're told that it starts from rest, and we're told that in a time of 4 seconds, it goes 3 times around. Well, 3 revolutions, if I multiply that by 1 and I write the number 1 as 2 pi radians, is the same as 1 revolution. So that's 1. I cancel out the revolutions and I get 6 pi radians. So now I have 1, 2, 3 pieces of information. In part A, we're asked to find the angular acceleration. Okay, so part A, angular acceleration is what? Now that makes the omega final the who cares. So I'm going to use the equation that doesn't have omega final in it because I don't know it, I don't want to know it, and so I should use the equation that doesn't have that. And that equation is this one here. Okay, and we know that the initial omega is 0, and so this is going to be 6 pi radians is equal to 1/2 alpha times 4 seconds squared. Now if I solve that for alpha, I'm going to get 12 pi radians divided by 4 seconds squared, and that turns out to be 2.36 radians per second squared. Okay. Now, part B asks, how far does the block drop in this time, in the 4 seconds? In other words, how far has it dropped linearly? Now you remember that we have a rolling condition. The rolling without slipping condition relates the linear motion of something to the angular motion of, say, a wheel. Now, if you think of this wheel as laying out line, it's very similar to a wheel going down the road, and if this wheel had, say, grease on it, you'd be laying down a linear line of grease down the pavement, okay, and just like you're laying out a fishing line here. Okay, so we can use the rolling condition, namely that the linear displacement is equal to the radius of the wheel times the angular displacement of the wheel. And in this case, since we're not going down the road, but we're going vertically, we'll change that to a delta y. And so that's going to equal the omega. Everyone see the mistake I made there? I sure do. It's glaring at me. Makes me feel bad inside. That's not the omega there. This is going to be related to the angular displacement. The angular displacement. My bad. Okay, you'll get a rebate on your tuition, I'm sure. So this is going to be 0.2 meters times 6 pi radians, and that's going to be 1.2 pi meters, and that turns out to be 3.77 meters. Okay, now things change. In parts C, D, and E, we find that a hand is suddenly introduced into this problem, the lobster hand, and that the block that was speeding up, you know, it started from rest, so it clearly was speeding up. You can't slow down from rest. It was speeding up as it approached the floor. And then the hand put a friction force. If this wheel is turning that way, then the friction force is going to fight that motion with a kinetic friction force. Okay? Now, as a result of that friction by the hand, the block that was moving fairly rapidly begins to slow. So if the block is starting to slow in its linear motion, it's dropped towards the floor, then the wheel is starting to slow in its rotational motion. Okay? Now, part C asks us for the direction of omega during this time during which the wheel is slowing down. Well, the wheel is still turning clockwise, but that's not a direction for omega. Remember, for omega, we use the right-hand rule. We let the fingers in our right hand go in the direction of that rotation, and our thumb points along the axis of rotation. In this case, it would be into the board. Okay, and so I would say by right-hand rule. Now, part D asks us for the direction of the angular acceleration alpha. Now, let me be clear. There is absolutely no right-hand rule for alpha. Okay? Right-hand rule is for omega. For alpha, we have to do some thinking. We have to say, is this wheel spinning faster and faster as time goes on, or is it spinning slower and slower as time goes on? And just like in linear motion, when something's speeding up, the velocity and the acceleration are in the same direction. We have the same situation with angular motion. In this case, because the wheel is slowing down, these two vectors, omega and alpha, have to be in opposite directions. I don't care which one's into the board and which one's out of the board. They just got to be opposite. So if omega is into the board, alpha has to be out of the board because it's slowing down. Now, the last part asked us to compare the torque by the string on this wheel to the torque by the hand. which one's bigger, or are they the same size? Now, you may be watching this video before you've watched the lecture on torque, and so this may be a difficult question. This may be something that you're not prepared to answer quite yet, in spite of your careful reading of the textbook that I know you've done. But let me just try to make it reasonable to you. Torque is what causes an angular acceleration, causes things to speed up or to slow down. Now, the torque exerted by the string on that wheel was obviously making it speed up. It started from rest and it got spinning faster and faster and faster. The friction from the hand is exerting a torque that's causing it to slow down angularly. Okay? Now, if the string were the only torque on the wheel, it speeds up. Okay, so clearly that one's causing it to speed up. If the torque by the hand, the friction, was equal to the torque by the string, one trying to speed it up, one trying to slow it down, then we would have uniform motion. The wheel would be turning at a constant rate. The block would be dropping at a constant rate, constant velocity. Okay, but that's not what's happening. Okay, that would be the case if these two torques were equal to each other. Well, clearly in this case, the torque by the hand is winning because it's not speeding up anymore. It's not going at constant speed anymore. It's slowing down. And so that means the torque by the hand has to be greater than the torque by the string. Okay, this has been homework set number 32. Thanks for tuning in.